versus elimination. So when you look at a reaction, to determine what the product is, right, you're going to need to think about whether this is a substitution or elimination. And it's helpful if you know if it's SN1 or SN2, and whether it's E1 or E2 if it's elimination. So to predict your products in the reactions, or to predict the reagents you're going to need to know whether it's substitution or elimination is occurring, and how that's occurring. So the book is pretty helpful about giving you some ways to look at this. And I'd say this is probably the way I've been doing it for, well, oh my gosh, 30 years. So if we look at reagent, first step is to look at your reagent, right? And to think about, is it a nucleophile? And is it strong? Is it weak? Would it be better determined as a base? Again, strong and weak. And there's some overlap here. So sometimes it's going to be pretty straightforward. If we had something like sodium azide, right? This is a good, strong nucleophile, and it's not basic. Right? If we look at something like sodium hydride, this is a strong base and a poor nucleophile. Okay. And the book helps out here. It gives you a nice chart with some of these to look at, and we'll look at that and decipher that. So we can categorize our reagents in this way. Sodium hydride, right, is a strong base and a weak nucleophile. Here in the middle, we have strong bases and strong nucleophiles, right? Here we have weak bases and strong nucleophiles. So these will do substitutions, but not eliminations. Here we have weak bases and weak nucleophiles, right? So these could do either, right? But they're probably not going to do an SN2. So let me make some notes, right? So probably SN1 or E1 products, right? Here, probably probably substitutions. Right here, probably eliminations. Probably I could say yes, eliminations. Sorry, for some reason my computer decided this was the time to update my entire calendar. So what you're hearing ringing. And then here we have strong bases and strong nucleophiles. Right here we're going to have, things like E2 and possibly SN2. Okay, so you do have some overlap in these. The DBN and the DUB, those are good organic bases. They're a little larger. Okay, that's why we use the abbreviations. Okay. The way those work is that we look at when they pick up that proton, right? So here's DBNU acting as a base, right? So it picks up the proton, so proton transfer, loss of the leaving group. But then what we have is resonance, right? So that nitrogen can resonate between, that positive charge resonates between the two nitrogens, right? So we got a resonance stabilized species. It's big and bulky, so it doesn't make a really good nucleophile, but it does make a great base. So if we look at this first window, if we have any of these three reagents, then we're going to have an elimination process occurring, right? Same thing here. If we have any of these reagents, we really are going to favor substitution. Even with the sulfurs, we're not going to get elimination, right? Now, these other two, that's where we start to get a little bit elimination substitution, but notice that the strong nucleophiles and bases favor the bimolecular, right? Because the stronger base, stronger nucleophile is involved in that step. And then the weaker, we favor SN1 and SN2. So the first step is to analyze your reagent. So what kind of reagent do I have there? Where is it on the continuum of strong base to weak base? Where is it on the continuum to strong nucleophile to weak nucleophile, right? Some other ones that I could add in here, strong nucleophile would be something like sodium nitrile. Sodium cyanide would be a strong, well, actually, they don't have a list for this one. Strong nucleophile. Right, that would be things like sodium nitrile, right, and sodium cyanide, right? They could pick up a proton if you added an acid solution, but in most cases, they're going to act as a nucleophile. So if you see one of these two, it's kind of like our strong bases. These are going to be, these are going to be substitutions. So you can use this chart as you go through, but you also have to think about what makes something a good nucleophile and good electrophile, a good nucleophile and a good base. So it's good to have the most common ones. The question on the chat, do we need to memorize? Well, this is the list to kind of start to learn, but notice that you've got the first three, but what do you notice about all of these? Well, we could all distill these down into RO minus, right? And then here, how do we distill this one down? Well, this one is halides and sulfur compounds, right? So whether it's neutral or positive. And then what are our weak nucleophiles and base? Well, that's my RORH, right? So with the lone pair. So you can learn that list, right? But the second two boxes really fall down into those things. This is a good list to remember, and this is a good list. So you can see things that are not on this list, but that goes back to understanding what good bases are from our previous chapter, and then what are good nucleophiles from this chapter. So you will need to analyze that. This is a good list to have at your fingertips. Use it, practice enough to where you've seen these enough that you'll recognize them. Okay. If we look at the next step, right? Next step is expected mechanism. Okay. And so what mechanism would you expect to happen? This one really comes out of the substrate. Remember that the biggest difference between the different mechanisms is the substrate. And again, the book does a pretty good job of this. These are charts that most organic chemists created years ago in our PowerPoints, but the book has a nice one here. So remember that our substrate, your substrate analysis gets you started really well, right? So this is your substrate. So is your substrate primary, secondary, or tertiary? If it is primary, secondary, tertiary, and you're dealing with a strong base, weak nucleophile, notice that they're all E2, right? Because in a strong base conditions, even a tertiary, because it has no steric hindrance, is going to be E2. If we look at primary, secondary, tertiary for a strong base, strong nucleophile, you can see here that this is where we have, in a primary, we're going to get mostly substitution. In a secondary, we're going to get a mixture of mostly elimination. But then when we get to our tertiary again, why? Because SN2 is really slow in a tertiary, right? So SN2 is not going to occur. So if we look at the tertiary, right, we can say that that's not SN2 because an E2 will be faster, right? Or even in the case of the weak base strong nucleophile, right? When we get to tertiary, then all of a sudden SN1 favors because the SN1 goes through carbocation favors tertiary. And then if we look at the last one, weak base, weak nucleophile, primary and secondary really are difficult to get them to react. I would add a caveat here to say stabilized secondary, right? So if we have an allylic position or a benzylic position, as we looked at last time, then potentially we could get, so if you see a secondary, check and see if it's got a pi bond one away, either a double bond or an aromatic. And then you can see here with tertiary, we get SN1 and E1. And so it doesn't give us a nice only SN1 or only E1, but we usually are going to get a mixture. Right? Okay, questions about this chart? What I'd say for this chart is not to memorize it, but be able to create it. So on your test, it is not appropriate to have any outside materials. I know you're taking this at your room, but you should have no outside materials. If you are following academic integrity, you're not. But that does not mean as soon as you start with your empty scratch paper there, that once you start your exam, you can't create some of these things. What I would tell you if you're taking this in person, and if you take Organic 2 in person and this question comes up, or if they have things like this, is to create this chart, right? So remember that strong bases are going to favor E2. That goes all the way down. Strong bases, strong nucleophiles is going to depend on the substrate. Weak bases, strong nucleophile, it's going to be SN2 if it can be. It'll be SN1 if it can't, right? And then weak bases really only work with tertiary in SN1 and E1. I think I had another photo with this one. My son had a birthday party. So yeah, here we go. You get to see all my photos. So here, if we see an example, so what you'll see, right, is a primary substrate. So what I'd say here, this looks like a strong base, strong nucleophile, right? That comes from this up here, right? That's an oxygen negative. So this is an oxygen negative, right? That's Na plus OH minus. Okay, I've got a primary substrate. For a primary substrate, right, it's low steric hindrance. So I would expect that this backside attack, right, is going to be favorable, and I get the SN2. Okay. This is not coming from the chart. This is coming from what we covered. If you understand the mechanisms, you can build the chart. If you understand the nucleophiles and bases, you can build the table, this table up here, right? So if you understand what we've been talking about for the last couple of weeks and even back to chapter 4, right, you can build these things out. That's the way to think about this. In the second one, we have, again, we've got a strong nucleophile, strong base, right? But now we're dealing with a secondary substrate. We got more sterics, right, on the backside. So when this comes into attack, right, we have the choice of pulling this off, right? Or I'm going to put another one here, pulling the proton off. Okay. In this case, right, the E2 is going to be more favorable because the secondary substrate is more sterically hindered and slows down the SN2. So the more steric slows it down, but E2 is not slowed down, right? We don't have the steric effect. When we get to tertiary, we have no SN2, right? Because the backside attack right, is so slow that E2 is going to be the major. We can even say it's so slow that we don't really see reaction. Right, let's look at a couple, and then we'll move on to the next section. So take some time, look at these two, think about what the reagent tells you, think about what the substrate is telling you, and then determine what the possible products would be, or what the major and minor product would be, what the favored products would be. Okay, let's take a look. So the first one, we have the sulfur negative, right? Sometimes it's useful to go ahead and show it out this way. That'll help you. So if you're not automatically seeing the sodium as positive and the sulfur is negative, please redraw, right? Anytime you have sodium, lithium, and potassium, put a positive on it. Whatever's next to it is negative, all right? So that sulfur compound, right, is going to be a good nucleophile or strong nucleophile, right? Weak base. Okay. And then here we look at a primary substrate. So what we have here is that this indicates that we're going to have substitution. The primary indicates that I'm going to have, you know, either E2 or SN2 together, but primaries really favor SN2s, or possibly E2, right? So SN2 favored, possibly E2. And when you put those two together, this says that what I'm going to get is substitution. And because I want y'all to learn this, I'm going to show this, put this up, even though there's no stereochemistry here, right? So I get SN2 substitution. So when we put these together, we get an SN2 substitution. Okay. Here, let's take a look at this one. Again, what do we have here? We have a weak base, weak nucleophile, right? That's suggesting that I'm probably looking at SN2, SN1 or E1, but only if the substrate can make a carbocation. Here I have a secondary carbocation. If this was a normal secondary carbocation, SN1 and E1 would not be very likely, but this is a stabilized secondary. Why? Because if I form a carbocation, I have this double bond here that will allow that to react to give me the resonance, right? So therefore, since I have a stabilized secondary, this is going to be SN1 and E1, and my products are going to be the alcohol and some of you may have said, well, why don't I get this alcohol? You do, but notice that these two are actually the same molecule, right? So you would get water attacking either of the two carbocation positions, but in this case, it's the same molecule. Okay. Now, the third thing we need to look at is regio and stereochemistry. So figuring out what the reagent is, figuring out what the expected mechanism is. The next is looking at regio and again, your book has a nice nifty chart, so there's no reason for me to create it again. So if we look at the regio and stereochemistry, what we need to be thinking about is what my mechanism is, right? So once I know what the expected mechanism is, that helps me figure out what's going to be occurring. So if I think my mechanism is SN2, I've looked at my reagent suggests SN2, my substrate suggests SN2. I could also add solvent, although solvent is usually further down. It won't change an SN2 to an SN1, but a solvent could speed up an SN2, right? So here we see nucleophile attacks at the alpha position, right? So we have to have direct attack at the alpha position. So we want to look up here, right? It has to be at that position. Okay, and the nucleophile replaces the leaving group in inversion. Again, this is not a chart to remember. This comes out of what we covered for the SN2 mechanism, right? And so that's, I showed the sulfur going up. For E2, the important part for E2 is that Zaitsev, right, is favored over Hoffman, right? But with a big bulky base, right, I can favor the Hoffman elimination, right? So Zaitsev over Hoffman, unless big bulky base. Okay, the process is stereoselective, right? This is the anti-paraplanar. Right, so we have to be careful of our beta position. If the beta position, beta hydrogen can't eliminate anti-paraplanar, then we don't get the right, we won't get that elimination. Okay. When we look at SN1, nucleophile attacks the carbocation, right? Because there is a carbocation, there can be rearrangement, right? So we have to watch out for rearrangement. And the nucleophile leaves the leaving group at a racemic mixture. So stereochemistry, we get racemic. When we go to E1, we get Zaitsev, right, is always favored. So this is only Zaitsevs. And then in the stereoselective process, trans will be favored over cis, but they don't have the same restrictions, right? So and this is due to the stability of trans over cis, right? But it has no real stereo control. So it's selected, but it's not specific. So you look at your reagent, figure out what your reagent's going to be, then look at your substrate. That'll help you determine, along with your reagent, what the most likely mechanism is. And then from that most likely mechanism, then we're going to pick what our regioselectivity is, and then what our stereochemical outcome is, right? There's lots of practice on this in the book. The best way to do this is practice over and over again. The book problems, there's a bunch of those there. I'll post the Action Center problems today, and then the sapling, if you did do that, is also uploaded. Section 12, we need to look at different leaving groups. So the first one is tosylate. You have a question? So when we look at the tosylate is this basic group. We have 3 main tosylates, and again, this little wiggly line here just means this is where it's attached. If we have a CH3 here, this is the mesylate. We can substitute that and put the toluol group on here. A little off of my drawing. Wiggly line again. This is the actual tosylate from the toluene substituent. And then the last one you'll see most common. This is trifluoro. This is known as a triflate. Used to be much more popular. You still see it, but it used to be the favored one. Tosylate is kind of the favored now. So mesylate, tosylate, triflate. What we need to think about is if this leaves, what happens is that the oxygen can delocalize So because we can delocalize that around, that makes this a very stable leaving group. So we can take stuff like this, OTS, which is the tosylate abbreviation, react that with sodium bromide. Right in here, the bromide is a better leaving group. I mean, the tosylate is a better leaving group than the bromide. So this can go forward to give me an SN2 type mechanism to give me this product. If we look at it this way, tosylates are very good at SN2. Right, so we have a good nucleophile, not a very strong base. Right, we've got a great leaving group, secondary position. This is going to give me favored SN2, which means I'll end up at the alpha position and I'll get inversion, right? So if we put all those pieces together, hopefully you've been working through these as we go, so this doesn't sound like I'm speaking Greek. We'll see how to make tosylates in the alcohol chapter. For now, you'll just see the OTS, or you'll see you know, OMS, or you would see OTF, triflate, right? So those are the abbreviations for tosylate, mesylate, and triflate. Tosylate is the one the book prefers, and again, over time, we've gone from mesylate to trifolate to tosylate. The other group we need to talk about here is alcohols. And again, we'll get to more alcohols in the alcohol chapter. But the thing to think about with alcohols is that the OH, right, is a bad or poor, let me use poor. I don't want to do an emotional judgment on it. It is a poor leaving group. Right. So when we look at alcohols, the thing to remember is that if that group left, right, so let's think about a tertiary position here. If this just left, right, we get the OH minus. It's a poor leaving group, so that doesn't occur. That's correct. Water is fine. I'll show you that in just a second. So if we take an alcohol and react it with something like sodium bromide, we're not going to get the reaction. But if we take that same alcohol and now react it with HBr, now I will get product plus water. The reason for this is that I'm actually activating my alcohol with to become water, right? So we protonate, so we do a proton transfer. Now I have water as the potential leaving group. So if we look here, right, that would be water. Now the bromine can come in an SN2 style, but since this is primary, now let's use the red color. Right. So water is a great leaving group, or good leaving group, very good leaving group, right? So therefore, when we look at alcohols, we're actually going to activate them to be leaving group with acid. What we see in chapter on alcohols is we can also turn an alcohol into tosylate. The book just does not talk about that now, so we'll look at it later. But it does, what it does talk about now is the fact that alcohols, OH minus is a poor leaving group, but water is a good leaving group. So that means that we can get certain reactions like eliminations to occur by adding strong acid, like concentrated sulfuric acid. Okay. Concentrated sulfuric acid will form the double bond. If we look at the mechanism here, we get a proton transfer. Then we get a, there's going to be, you'll see that we're generating water in here. Sulfuric acid always has a little bit of water in here. That's why we said concentrated. So water is the most likely base in the solution. It then pulls off the proton, forms a double bond, right? And what I end up with is water plus then the acid, right? So the acid is a catalyst, it gets the reaction going, but I generate the acid and water in the process. So I use an acid, I gain an acid, and I kick off water to give me my final product. So with alcohols, it's reacting with acids. The acids activate those alcohols. So that's why we can have substitution of alcohols with the acid halides. So HBr, HCl, HI. And then this one, this is known as a dehydration. And the reason that works is we get a proton transfer to give us the product. Okay. So the question, OH minus is a bad leaving group, but water is good. Actually, it's a good leaving group. It's not fine. It's good. Okay. Okay. The last step here is to introduce synthetic strategies, and the book uses these throughout. It's going to be the last section of every chapter. And what we're really doing here is thinking about retrosynthesis. So if we think about the one we just looked at, you know, this would be known as my starting material. And this would be our target molecule. Okay. And the way you've seen these reactions so far, because we always think about starting from point A and going to point B, right? But what's most important, if we were going to travel, and let's say that we wanted to go and visit, you know, who wanted to go and visit your grandma, and your grandma happened to live in Ada, what's kind of the most important thing you need to know to get to Ada? Well, where Ada is. Is it more or less important to know where Ada is or to know where you are? Well, you do need to know where you are, right? But to start with, you're going to need to know where Ada is, right? If we think about lumber, right? So if I want to build a house, that's my target. My target is to build a house, not to use a bunch of 2x6s and 2x8s and some drywall, right? But once I know what house I want to build, I'll know what I can start with to make that house. So that's what the retrosynthesis is really thinking about, is that in chemistry, yes, we may have a bunch of starting materials sitting around and we may want to figure out a way to use it. But in most cases, what we really want is the target. We want the new drug, we want the new material, we want the new whatever, right? We want to make something like a house or a car. And then we have to figure out what can we use to make that. So what retrosynthesis does is it says that we're going to invert this, right? And we're going to look at, if we want to make this molecule, right? Then big fat arrow, this is a retrosynthesis arrow. How do I make it? So this is my target. And then over here, right? And I could potentially put this as my starting material. And what the retrosynthesis would be is, okay, how do I end up making this, right? How do I make that molecule? Another example would be if we looked at this, right? And I said, we're going to start by starting with this starting material. Well, that starting material, I've got to react that to form a halide. And then that reaction, we're going to eliminate that to give me my double bond, right? So I've started and I've done a radical reaction, and then I've done an elimination. So the retrosynthesis arrow is going to be one you see. You should notice it because it's a big fat arrow instead of the normal. And what you need to remember about it is that what is on your left now is your target. What is on your right is a suggested starting material. We've gotten to the point now where we have lots of possible synthetic means, right? So if we look at what you've just learned in this chapter, you've learned all of these, right? So we can start with an alkyl halide. We can add sodium cyanide, right, to get me a nitrile. I can add the acetate to get me an ester. I can add a sulfur compound to get to the thiol. I can add an methoxide or an alkoxide to get to an ether. I can do an elimination, right, with a base to get to an alkene. I can eliminate a tosylate, right, to get to an alkene. I can turn an alcohol into an alkyl halide. I can turn an alkyl halide into an alcohol. Oh, and look, here's that reaction. So why don't we go ahead and introduce that one? They showed it here. I didn't see it in the book. So actually, since they use the tosylate, we'll use the tosylate. Right. What's happening here is remember that sulfurs are hypervalent. So the lone pair is attacking the sulfur. The pyridine is this molecule. The pyridine acts as what we call a proton sink. Proton sink is just something that will take a proton. So pull that proton off. And then we get loss of our chloride. Okay. So alcohol to tosylate. So we can see what I was trying to show up here, right, is that we've got a lot of different reactions. The book also shows this one. All right, so you can see alcohols to alkenes. So we can go one step here, but then if we go one more reaction, right, then we can use the T-butoxide to get our Hoffman product. If I just use sodium hydroxide, right, a not a bulky base, we can get the Zaitsev product. If we just gone directly with this, we're going to go E1, right? This one has to be E1. Right, we're going to get Zaitsev only because it only can do that. We could potentially have gone and made this the tosylate first, so TSPY, and then gone to ZF, or taking the tosylate and gotten the T-butoxide. So where we're getting to now is that when we look at retrosynthesis, we can have multiple ways to get to the same product, right? So let's take a look at a couple of those. So I want to form this. And let's say from that. So let's take a second, look at this one. Oh, not B, BR. We are getting close on time, so let's stop. I've got 4 carbons over here. That's one way to analyze this. So I have 4 carbons. So if I look over here, right, where are my 4 carbons? So 1, 2, 3, 4, 1, 2, no, 1, 2, 3, 4. So it looks like that these 4 carbons here are these 4 carbons there, which then means that this is the part that I can add. And since it's not giving me that, I can add it, right? So I can add anything I want to get the reaction, as long as the reaction is a viable reaction. So therefore my reaction, my retrosynthesis would be to start with the bromide. I need to add an alkoxide. And since this is primary and this is a strong nucleophile strong base, since that's primary, I'm going to get an SN2 reaction, right? And that will give me my product. So really all I need to do is add sodium ethoxide to get me to the ether. So the answer would be to figure out what reagents and what steps you would need to get to the product. Okay, let's try another one. Oops. Again, didn't leave us a whole lot of time to practice these. In this one, if we had tried to do this, would there be a problem? Well, this would probably go through SN2, but it also could go through SN1, right? So I might end up with this as the major product, but I may also end up with a little bit of this. The reason for that is once I've formed this, right, could water have come in, right, and kick that off to create this? Well, yes. And all of a sudden I end up with a mixture. So what I'd want here is a cleaner process where I'm not going through the acid. So I would start with my tosyl chloride. That gives me a great leaving group, right? And then instead of using HBr and protic solution, which would favor SN2 and give me a lot of water, I can use sodium bromide in a aprotic solvent, which will allow me to get selectively the inversion. Okay. All right, we've run out of time. So that's synthetic strategy. There's some of those in your online homework and on the book homework. There'll be some of those on the Action Center. So if you have any questions, let me know.